Okay, so we talked about Newton's first law, which sometimes is also called the law of inertia. And that was basically just an object tends to want to keep doing what it's doing. If it's moving, it wants to keep moving. You have to force it, put a force on it to change that motion. If it's not moving, it wants to continue to not move, and you have to put some net external non-zero force on it in order for it to move. So let's talk about momentum and Newton's second law. So first off, what is momentum? Momentum can be described as how much something moves. We've talked about how far something moves. We talked about how fast something moves, but we kind of want to quantify how much does it move, which kind of sounds like a strange question. But Isaac Newton kind of decided that the best way to quantify this how much does an object move question was to take its mass and multiply it by the velocity. And that seems like a relatively reasonable way to define this. If you have a 1/10 kilogram of an object moving towards you at 20 meters per second, or 10 meters per second, it might not have much of an effect. But if you have a 20 kilogram object moving at you at 10 meters per second, that's a significant difference. We'd expect a bigger number for that if we're talking about quantity of motion. And he called this momentum. So the equation for momentum looks like this. We have P is going to be our symbol for momentum equals mass times velocity. But since we have this velocity here, and this is a vector quantity, our momentum is a vector quantity as well. So momentum is a vector. It has a direction. If I have an object moving in some certain direction, it also has momentum in that direction. It's going to have the same direction as the velocity. So let's take a look at the units of momentum. If momentum is mass times velocity, and mass is in units of kilograms, and velocity is in units of meters per second, well, then momentum is in units of kilogram meters per second. So this is the SI, this is a combination of the SI units of mass and distance and time here. And these are our units for momentum. And this brings us into Newton's second law. Newton's second law is probably familiar to you, and it looks like this. So Newton's second looks like this. F equals, we should say the net force, the total force, equals what? It's the rate of change of momentum with respect to time, right? So that's probably not the form that most people are used to hearing, but this is the calculus-based physics class, and so we can describe it as this way. The force on an object is the rate of change of the momentum. And you may be asking, how does this get back to ma that I'm used to? Well, let's take a look at that. First off, force has a direction. If it's the derivative of a vector quantity, the force is also a vector quantity. And of course, we know our acceleration here is a vector quantity. So let's take a look at this momentum and see if we can't get this mass times acceleration that seems so familiar. Well, the derivative of momentum with respect to time is the same thing as the derivative with respect to time, and we can just take our momentum equation up here. Momentum is mass times velocity. Okay? Now, if we're in a situation where our mass is staying constant, which at first seems kind of like an odd thing to say, but in later topics in physics, we'll have situations where the mass of an object is not constant. An object can be moving so fast that its mass shifts and varies. So dp dt equals the derivative of mass times velocity, but if mass is constant, then we can just move that out of the derivative. It's the constant rule of derivatives. So this is the same thing as the mass times the derivative with respect to time of velocity. But what's the derivative with respect to time of velocity? That's just the acceleration. dv dt is just the acceleration. So we have ma, and we said this was the total force. So this gets us our familiar F equals ma result from Newton's second law. So what are the units of force? It's always good to take a look at the units when we discuss or introduce a new quantity. So up here with the momentum, we saw that it was just kilogram meters per second. But what about force? So the force is ma, so we'll rewrite it down here. F net is a velocity equals mass times our acceleration, is a vector, equals mass times our acceleration vector. Well, what are the units of mass? And so we'll just take a look at the units. Well, mass is in units of kilograms, and acceleration, if we multiply by acceleration, it's in units of meters per second squared. And so we can just combine this to get kilogram meters per second squared. Now, with momentum, we don't have a special name for this. This is just a unit of momentum is a kilogram meter per second. But when we have force, there is a special name for this, kilogram meters per second squared. And we represent it by a capital N. And this capital N is a Newton. So the unit of force, the units of force are newtons, named after Isaac Newton. And so 1 Newton is the force that you need to take a 1 kilogram mass and accelerate it at 1 meter per second squared. So let's write that down. 1 Newton is required to accelerate a 1 kilogram object at 1 meter per second squared. So if we take a 1 kilogram object, and let's say it's starting at rest, and after 1 second, we want it to be going 1 meter per second. After 2 seconds, we want it to be going 2 meters per second. After 3 seconds, we want it to be going 3, and so on and so forth. Every second, we want to increase its velocity by 1 meter per second. If that object weighs 1 kilogram, the amount of force we're going to have to continually apply to this object is exactly 1 Newton. So the Newton is the SI unit of force. I think I've mentioned SI units once or twice. The SI units can be thought of as the international system. The actual abbreviation is French, and I'm not going to try to pronounce it, but it basically means the international system. And so these units are just kind of a standard system of units that we use and that we will continue to use. And it's the seconds instead of the minute, it's the meter instead of the foot, it's the kilogram instead of the gram. But we can always go between different systems, and just to get a couple more units of force, we can also measure force in pounds, which might seem like an odd thing. So pounds are a unit of force. We think of mass and weight kind of interchangeably from day-to-day life, but there's actually a difference. We'll talk about that more when we get into gravity, which is one of the fundamental forces, but a weight of an object has to do with the force of gravity acting on it, and the mass of an object is kind of like an intrinsic how much of the object is there. But we'll get into that more with gravity. So 1 pound is about, it's pretty much equal to about 4.448 newtons. So that's a pound. And then we can talk about a dyne. A dyne is an extremely small measurement of force used in very small systems. And a dyne, 1 dyne, is about 10 to the negative 5th newtons. That's extremely small. That's about 1/100,000th of a newton. So just like with length or time, we can measure this in different ways. But for our purposes, when we're converting units and we're trying to get everything down to a basic system, we're most often going to use the newton.